Tonight, we're going to talk about a particle so ghostly that trillions of them are passing through your body right now, and you will never feel a single one. Neutrinos. For decades, physicists thought they understood these particles perfectly. The Standard Model, the most successful theory in the history of science, predicted exactly how neutrinos should behave. And then, something went wrong. Experiments started showing that neutrinos were doing something the Standard Model said they couldn't do. They were changing identity mid-flight, transforming from one type into another as they travelled through space. And that simple observation, confirmed beyond any doubt, implies something that shakes the foundations of particle physics. Neutrinos have mass. And that mass, tiny as it is, does not fit cleanly into the theory that explains almost everything else. This is the crack, and it might be the biggest clue we have to what lies beyond. Before we dive in, if you find this kind of deep exploration of physics interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. The Standard Model of particle physics is, by almost any measure, the most successful scientific theory humans have ever built. Not just good, not just approximately right. It is a framework so precise, so rigorously tested, so stunningly accurate in its predictions that it borders on absurd. Over the past 50 years, physicists have tested this theory in thousands of experiments across dozens of countries, using machines that cost billions of dollars and push engineering to its absolute limits. And almost every single time, the Standard Model has gotten the answer right. It has predicted the existence of particles before anyone ever detected them. It has calculated the outcomes of collisions between subatomic particles to more than 10 decimal places of accuracy. There are quantities in physics where the Standard Model's prediction and the experimental measurement agree to better than 1 part in a billion. That is not a rough estimate. That is not a ballpark guess. That is a prediction so precise that if you compared it to measuring the distance between New York and Los Angeles, the margin of error would be smaller than the width of a human hair. No other theory in the history of science even comes close to that level of agreement between prediction and observation. And yet, this astonishingly successful theory has a crack in it, a subtle flaw, a place where the elegant mathematics do not quite match what nature actually does. And that crack involves one of the strangest, most elusive, and most mysterious particles in the universe, the neutrino. To understand why this matters, you need to understand what the Standard Model actually is and why physicists trust it so deeply. Because the depth of that trust is what makes the crack so important. When a theory has been right about almost everything for half a century and then gets one thing wrong, that one thing demands your full attention. The Standard Model is a mathematical framework that describes the fundamental building blocks of the universe and the forces that govern how they interact. Everything you have ever seen, touched, or experienced, every star in the sky, every atom in your body, every beam of light that has ever crossed the cosmos, all of it is described by the Standard Model. At its core, the theory says the universe is made of a relatively small number of fundamental particles, 17 of them depending on how you count. These are not atoms or molecules. These are the particles that atoms and molecules are made of, the smallest, most basic ingredients of physical reality as we currently understand it. These 17 particles fall into 2 broad categories. There are the matter particles, which make up the physical stuff of the universe, and there are the force-carrying particles, which govern how that stuff interacts. The matter particles are called fermions, and they come in 2 families. The first family is the quarks. There are 6 types of quarks arranged in 3 pairs. The up quark and the down quark form the first pair. These are the ones that matter most for everyday reality, because protons and neutrons, the particles that make up atomic nuclei, are built from up and down quarks. A proton is 2 up quarks and 1 down quark held together. A neutron is 1 up quark and 2 down quarks. Everything you see around you, every solid object, every drop of water, every breath of air, it is all protons and neutrons at its core, which means it is all up and down quarks. The other 4 quarks, the charm, strange, top, and bottom, are heavier and less stable. They appear in high-energy collisions and exotic conditions, but they decay quickly into the lighter quarks. They existed in abundance in the early universe, fractions of a second after the Big Bang, but today they show up mainly in particle accelerators, where physicists smash particles together at incredible energies and briefly recreate those extreme conditions. The second family of matter particles is the leptons, and this is where neutrinos live. There are 6 leptons, also arranged in 3 pairs. The electron is the most familiar. It is the lightweight, negatively charged particle that orbits atomic nuclei and makes chemistry possible. Every chemical bond, every electrical current, every signal traveling through your nervous system, all of it involves electrons. The electron has 2 heavier cousins. The muon, which is about 207 times heavier than the electron, and the tau, which is about 3,490 times heavier. Both the muon and the tau are unstable. They decay rapidly into lighter particles. You do not encounter them in daily life. Each of these 3 charged leptons has a partner, and those partners are neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. 3 types or flavors of neutrino, one paired with each charged lepton. This is the structure of the matter side of the Standard Model: 6 quarks and 6 leptons, arranged in 3 neat generations, each generation heavier than the last. The pattern is elegant, almost too elegant, as if nature designed a periodic table for its most fundamental particles. Then there are the force carriers, the particles responsible for transmitting the fundamental forces. The universe, as described by the Standard Model, has 3 forces built into it. Electromagnetism is carried by the photon, the massless particle of light. Every time a light bulb shines, every time a magnet sticks to your refrigerator, every time 2 charged particles attract or repel, photons are involved. The strong nuclear force is carried by particles called gluons. This is the force that holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei. It is extraordinarily powerful at short distances, but its range is tiny. It operates at the scale of atomic nuclei and essentially vanishes beyond that. Without the strong force, no nucleus could hold together. No atom heavier than hydrogen could exist. No stars, no planets, no chemistry, no life. Then there is the weak nuclear force, carried by 3 particles: the W+ boson, the W- boson, and the Z boson. These are massive particles, much heavier than protons. The weak force is responsible for certain types of radioactive decay. It is the force that allows a neutron to transform into a proton, emitting an electron and a neutrino in the process. This is the force behind beta decay, the process that powers some forms of nuclear energy and plays a role in the fusion reactions inside stars. And finally, there is the Higgs boson, which is in a category of its own. The Higgs boson is associated with the Higgs field, a field that permeates all of space. When certain particles interact with the Higgs field, they acquire mass. Without the Higgs field, electrons would be massless. They would fly around at the speed of light and never settle into orbits around nuclei. Atoms could not form. Chemistry would not exist. You would not exist. The Higgs field is what gives the fundamental particles their mass and allows the complex, structured universe we live in to exist. That is the Standard Model. 17 particles, 3 forces, and 1 field that gives mass to the others. It sounds manageable, almost simple. But the mathematics behind it is extraordinarily complex, and the theory's predictions are extraordinarily precise. And that precision is what makes the Standard Model so special. This is not a theory that gives vague, hand-waving answers. It gives numbers, specific, exact numbers that you can go and measure. And when physicists go and measure, the numbers match. The magnetic moment of the electron is one of the most precisely measured quantities in all of science. The Standard Model predicts this value to more than 10 significant digits. The experimental measurement agrees with that prediction to more than 10 significant digits. Think about that for a moment. A theory written on paper, built from mathematical equations, predicts a property of an electron to an accuracy of better than 1 part in 10 billion. And then an experiment, conducted with painstaking care over years, confirms that prediction digit by digit. The theory and the experiment agree so precisely that if you wrote both numbers out, they would match for the first 10 digits before showing any difference at all. That is not luck. That is a theory that understands something deep about how nature works. The crowning achievement of the Standard Model came in 2012, when physicists at CERN, the European Organization for Nuclear Research, announced the discovery of the Higgs boson. This particle had been predicted almost 50 years earlier, in 1964, by several physicists including Peter Higgs and François Englert. The theory said this particle must exist for the Higgs field to work, but no one had ever seen it. For decades, physicists searched. They built increasingly powerful particle accelerators, smashing particles together at higher and higher energies, looking for the telltale signature of the Higgs. The Large Hadron Collider, a circular tunnel 17 miles in circumference, buried beneath the border of Switzerland and France, was built in large part to find it. Thousands of physicists and engineers from over 100 countries worked on the project. The machine cost roughly $10 billion and took over a decade to construct. And on July 4, 2012, they found it. The Higgs boson appeared exactly where the Standard Model said it should be, with the properties the Standard Model predicted. It was a triumph, a vindication of decades of theoretical work and billions of dollars of experimental effort. The Standard Model was complete. Every particle it predicted had now been found. Every measurement confirmed its equations. And that is what makes the neutrino problem so striking. Because this theory, this monumentally successful theory that has survived every test physicists have thrown at it, made a very specific assumption about neutrinos. It assumed they have no mass. In the original formulation of the Standard Model, neutrinos are massless. They travel at the speed of light, just like photons. They have no rest mass whatsoever. And for a long time, this seemed perfectly reasonable. There was no experimental evidence that neutrinos had mass. Every measurement of neutrino behavior was consistent with them being massless, and there were good theoretical reasons to expect it. The mechanism that gives other particles mass, the Higgs mechanism, requires particles to exist in two forms, a left-handed version and a right-handed version. This has to do with a property called chirality, which describes how a particle's spin relates to its direction of motion. For electrons, both forms exist. For quarks, both forms exist. The Higgs field interacts with both forms and generates mass. But for neutrinos, as far as anyone could tell, only the left-handed version existed. No experiment had ever detected a right-handed neutrino, and without a right-handed neutrino, the Higgs mechanism has nothing to work with. It cannot generate mass for a particle that only comes in one form. So the simplest, cleanest version of the Standard Model simply declared neutrinos massless and moved on. And this made physical sense, because neutrinos are already the oddest particles in the Standard Model. Every other matter particle in the theory participates in multiple forces. Quarks feel the strong force, the weak force, and electromagnetism. Electrons feel the weak force and electromagnetism. But neutrinos feel only the weak force. That is it. They carry no electric charge, so they are completely invisible to electromagnetism. They are not quarks, so the strong force ignores them entirely. The only force in the standard model that can touch a neutrino is the weak force, and the weak force is weak. It is not called the weak force as a nickname, it is genuinely feeble. The particles that carry it, the W and Z bosons, are heavy, roughly 85 and 97 times heavier than a proton respectively. Heavy force carriers mean the force has an incredibly short range. It operates only at distances smaller than an atomic nucleus. And even within that tiny range, the probability of a weak force interaction happening is extremely low. This is why neutrinos are ghostly. It is not a metaphor, it is a physical reality. Because neutrinos only interact through the weak force, and the weak force is fantastically feeble, neutrinos almost never interact with anything. A neutrino can pass through the entire Earth without touching a single atom. Not because it is small, though it is, but because the only force it responds to barely operates at all. If you took a beam of neutrinos at the energies produced by the Sun and aimed them at a solid wall of LED 1 light-year thick, roughly 6 trillion miles of solid metal, about half the neutrinos would still make it through the other side without interacting. That is not an exaggeration. That is what the mathematics tells us. A light-year of solid LED, and neutrinos barely notice it is there. Right now, as you are listening to this, about 100 trillion neutrinos from the Sun are passing through your body every single second. They enter one side of you and exit the other, and neither you nor the neutrinos are affected in any measurable way. They are passing through the walls of your room, through the floor beneath your feet, through the entire planet below you. At night, when the Sun is on the other side of the Earth, the neutrinos pass through the entire planet and then through you, undisturbed. The Earth is essentially transparent to them. And it is not just solar neutrinos. Neutrinos are produced in nuclear reactors, in cosmic ray collisions in the atmosphere, in the cores of exploding stars, and in the Big Bang itself. They are everywhere. The universe is flooded with them. But because they almost never interact, they are almost impossible to detect. The neutrino was first proposed in 1930 by the physicist Wolfgang Pauli, and even he was embarrassed by the idea. He suggested the particle in a letter to colleagues, apologizing for proposing something that might never be detected. He called it a desperate remedy to explain a problem with energy conservation in beta decay. When certain radioactive nuclei decayed, emitting an electron, the electron did not carry away all the expected energy. Some energy was missing. Either energy conservation was wrong, which would have been a disaster for all of physics, or an invisible, undetectable particle was carrying away the missing energy. Pauli chose the invisible particle. He did not like it, but the alternative was worse. Pauli originally called his proposed particle the neutron because it was electrically neutral. But 2 years later, in 1932, the British physicist James Chadwick discovered a much heavier neutral particle inside the atomic nucleus, and that particle claimed the name neutron. Pauli's tiny, massless ghost needed a new name. It was the Italian physicist Enrico Fermi who provided one. He called it the neutrino, an Italian diminutive meaning little neutral one. The name stuck. It captured something essential about the particle. It was neutral, it was little, and it was almost nothing at all. For 26 years, the neutrino remained theoretical, a placeholder in equations, a ghost invoked to balance the books. Many physicists suspected it might never be found. Pauli himself was so doubtful that he reportedly wagered a case of champagne that no one would ever detect his particle. The odds seemed to be on his side. How do you detect something that passes through the entire Earth without interacting? How do you catch a particle that is, by design, invisible to every instrument you could build? It seemed like an impossible task. And then, in 1956, Frederick Reines and Clyde Cowan succeeded in detecting neutrinos for the first time, using the nuclear reactor as their source. The reactor produced enormous numbers of antineutrinos, and Reiners and Cowan built a detector sensitive enough to catch the rare occasions when one of these particles actually interacted with matter. The experiment was conducted at the Savannah River nuclear plant in South Carolina, using a detector placed close to the reactor core to maximize the antineutrino flux. Even with a powerful reactor producing trillions of antineutrinos every second, the detection rate was agonizingly low. But it was enough. They sent a telegram to Pauli, informing him his particle was real. Pauli, by all accounts, was delighted. He owed someone a case of champagne. The neutrino had been found. But even after detection, neutrinos remained the strangest particles in the Standard Model. They are the lightest fermions by a staggering margin. The electron, the lightest charged particle, has a mass of about 0.511 mega-electron volts. The lightest neutrino has a mass so small we still cannot pin down its exact value, but it is less than 1 electron volt. That means the electron is at least 500,000 times heavier than the heaviest neutrino, and possibly millions of times heavier than the lightest. No other pair of fermions in the Standard Model has such an extreme mass ratio. The top quark, the heaviest fermion, has a mass of about 173 giga-electron volts. That is roughly 340,000 times heavier than the electron. The gap between the top quark and the electron is enormous, about 5 orders of magnitude. But the gap between the electron and the neutrino is at least another 5 or 6 orders of magnitude. Neutrino masses are absurdly, inexplicably tiny compared to every other particle that has mass. And here is where the crack begins to open. Because we now know, beyond any reasonable doubt, that neutrinos do have mass. The Standard Model said they were massless. Nature said otherwise. This is not a minor discrepancy. This is not a small correction to a number somewhere in the theory. This is a qualitative failure. The Standard Model, in its simplest and most elegant formulation, contains no mechanism to give neutrinos mass. It was built on the assumption that they are massless. It was tested and confirmed for decades under that assumption. And that assumption turned out to be wrong. Neutrinos have mass. Small mass, absurdly small mass, but mass nonetheless. And that mass has consequences that ripple through the entire theoretical framework. How do we know neutrinos have mass? Because of something extraordinary that neutrinos do, something the massless Standard Model neutrinos could never do. They change. They transform from one flavor into another as they travel through space. An electron neutrino produced in the core of the Sun can arrive at Earth as a muon neutrino or a tau neutrino. A muon neutrino created in the atmosphere by a cosmic ray collision can arrive at a detector on the other side of the planet as a tau neutrino. The flavors shift. They oscillate. And as we will see, this oscillation is only possible if neutrinos have mass. This phenomenon, called neutrino oscillation, was not a theoretical prediction that experimenters confirmed. It was the opposite. It was a mystery that experimenters stumbled into, a discrepancy that refused to go away, a problem that haunted physics for decades before it was finally understood. Physicists were not looking for evidence that the Standard Model was wrong. They were looking for neutrinos from the Sun and finding the wrong number. Far too few. And that shortage, that persistent, stubborn deficit of solar neutrinos, turned out to be the first clue that something fundamental was missing from our understanding of particle physics. The Standard Model is not wrong. Let me be clear about that. It is spectacularly right about almost everything. Its predictions have been confirmed to extraordinary precision across a vast range of phenomena. But it is incomplete. The crack is real, and the neutrino, this ghostly, barely detectable, almost massless particle, is what exposed it. When a theory as powerful and precise as the Standard Model gets something wrong, it does not mean the theory is useless. It means the theory is pointing at something deeper. It means there is more to discover. In the neutrino, the particle that barely interacts with anything, the particle that can pass through a light year of solid lead without stopping, may be the single most important guide we have to whatever comes next. The story of how physicists discovered neutrino oscillation is a story that stretches across decades, across continents, and deep underground, into mines and tunnels where enormous detectors waited in darkness for the faintest possible signal from the most elusive particle in the universe. It begins with the Sun and a physicist who spent nearly 30 years staring at an apparent impossibility and refusing to accept that his experiment was wrong. Deep inside the Earth, in an old gold mine in South Dakota, a physicist named Ray Davis Jr. spent nearly 3 decades trying to count neutrinos from the Sun. What he found, or rather what he did not find, became one of the most important and most frustrating puzzles in 20th century physics. His experiment worked. His detector was functioning correctly, his chemistry was meticulous, but the numbers were wrong. He kept finding roughly 1/3 the number of neutrinos that the Sun should have been producing. 1/3. Not half, not 90%, 1/3. For years, people assumed there had to be an error somewhere. Either Davis was making a mistake in his measurements, or the theoretical models of how the Sun works were wrong. Almost nobody considered a third possibility, that the neutrinos themselves were doing something nobody expected. To understand why Davis found too few neutrinos, you first need to understand why he expected a specific number in the first place. The Sun is a nuclear furnace. Deep in its core, where temperatures reach about 15 million degrees and the pressure is roughly 265 billion times Earth's atmospheric pressure, hydrogen nuclei are being fused together into helium. This is the process that powers the Sun. It has been doing this for about 4.5 billion years and will continue for roughly another 5 billion. The basic reaction takes 4 hydrogen nuclei, which are just protons, and through a series of steps fuses them into one helium nucleus, which contains 2 protons and 2 neutrons. Along the way, some protons must convert into neutrons. This happens through the weak force, and every time a proton converts into a neutron, 2 things are produced: a positron, which is the antimatter partner of the electron, and an electron neutrino. The neutrino carries away a portion of the energy released in the reaction. It is a necessary byproduct of the fusion process. No neutrinos, no fusion. No fusion, no sunlight. Physicists in the 1960s had developed detailed mathematical models of the Sun's interior. These models, called solar models, described the temperature, pressure, density, and chemical composition at every depth inside the Sun. Using these models and the known physics of nuclear reactions, they could calculate exactly how many neutrinos the Sun should be producing, and at what energies those neutrinos should emerge. The calculation was not simple, but it was well understood. The nuclear physics was solid. The solar models had been refined over decades. The prediction was clear. The Sun should be producing a specific, calculable flux of electron neutrinos. And Ray Davis Jr. set out to measure that flux. His detector was extraordinary for its time. It was located nearly a mile underground in the Homestake gold mine in Lead, South Dakota. The depth was essential. Cosmic rays, high-energy particles constantly bombarding Earth from space, would overwhelm any neutrino detector on the surface. But cosmic rays cannot penetrate a mile of solid rock. Nearly a mile of Earth above the detector filtered out almost everything except neutrinos, which passed through rock as if it were not there. The detector itself was a tank containing roughly 100,000 gallons of perchloroethylene, a common dry cleaning fluid. This fluid is rich in chlorine atoms. On exceedingly rare occasions, an electron neutrino would strike a chlorine-37 nucleus and convert it into an argon-37 nucleus. Davis would then extract the argon atoms from the tank and count them. Each argon atom represented one detected neutrino. The numbers were staggeringly small. Out of the roughly 100,000 gallons of fluid, containing an enormous number of chlorine atoms, Davis expected to detect about 1 or 2 neutrino interactions per day. That is how rarely neutrinos interact. You fill a swimming pool with detector fluid, put it a mile underground, wait an entire day, and you catch 1 or 2 neutrinos. Maybe. On some days, nothing. The experiment ran for cycles of several weeks, after which Davis would flush the tank and extract whatever argon had accumulated. He developed chemical techniques so sensitive he could extract a handful of atoms from 100,000 gallons of liquid. It was painstaking, meticulous work that pushed the boundaries of radiochemistry. And the result was consistent year after year, run after run. Davis detected roughly 1/3 the expected number of neutrinos. Not 0, not the full amount, about 1/3. This became known as the solar neutrino problem, and it persisted from the late 1960s through the 1990s. Davis first published his results in 1968. For the next 3 decades, the solar neutrino problem refused to go away. The physics community was skeptical. Most people assumed the problem was either with Davis's experiment or with the solar models. Perhaps the interior of the Sun was slightly cooler than the models predicted, which would reduce the neutrino flux. Perhaps some nuclear reaction rate had been measured incorrectly in the laboratory, throwing off the predictions. Perhaps Davis's chemical extraction process was not as efficient as he believed, and he was missing some of the argon atoms. Each of these possibilities was investigated carefully over the years. Solar models were refined and improved. Nuclear reaction rates were remeasured with better precision. Independent checks were performed on Davis's chemistry, and one by one, each potential source of error was either ruled out or shown to be far too small to explain the factor of 3 deficit. Meanwhile, a handful of theorists had proposed a radical alternative explanation. The idea originated with a Soviet physicist named Bruno Pontecorvo as far back as the late 1950s, and it was further developed in subsequent decades. Pontecorvo suggested that neutrinos might be able to change from one flavor to another as they travel. An electron neutrino produced in the Sun might transform into a muon neutrino, or a tau neutrino during its journey to Earth. If this were true, it would explain the solar neutrino problem beautifully. Davis's detector could only detect electron neutrinos. It was completely blind to muon neutrinos and tau neutrinos. If the Sun's electron neutrinos were transforming into other flavors during the 8-minute trip from the Sun to the Earth, they would still arrive, but they would arrive wearing a different identity. Davis's detector would not recognize them. They would pass right through his tank of cleaning fluid without triggering a single chlorine to argon conversion. The Sun would be producing exactly the right number of neutrinos, but by the time they reached Earth, 2/3 of them would have changed into flavors that were invisible to the experiment. It was an elegant idea, but it had a profound implication that made many physicists uncomfortable. Neutrino oscillation, as this flavor-changing phenomenon came to be called, is only possible if neutrinos have mass, and the standard model said they did not. To understand why mass is required for oscillation, you need to understand a strange feature of quantum mechanics. In the quantum world, particles do not always have definite identities in the way we imagine. An electron neutrino is not necessarily a single, indivisible thing. It is a quantum state, and that quantum state can be described in different ways depending on what you are measuring. There are 2 different ways to describe neutrinos, and they do not line up with each other. The first way is by flavor. This is the description that matters when neutrinos interact with other particles. When a neutrino is produced in a weak force interaction alongside an electron, it is by definition an electron neutrino. When it is produced alongside a muon, it is a muon neutrino. Flavor is determined by the interaction. It is the label the neutrino wears when it is born or when it is detected. The second way is by mass. Neutrinos, if they have mass, come in 3 mass states. Call them mass state 1, mass state 2, and mass state 3. Each has a specific, definite mass, though we do not yet know the exact values. These mass states are the versions of the neutrino that travel through space in a well-defined way. Each mass state has a specific energy and momentum for a given speed, and each propagates as a quantum wave with a specific wavelength. Here is the critical point. The flavor states and the mass states are not the same. An electron neutrino is not mass state 1. A muon neutrino is not mass state 2. Instead, each flavor state is a quantum superposition, a mixture of all 3 mass states. When an electron neutrino is produced in the Sun, what actually emerges is a specific combination of mass state 1, mass state 2, and mass state 3, mixed together in particular proportions. All 3 mass states are present simultaneously, layered on top of each other in a precise quantum blend. Now, here is where mass becomes essential. If all 3 mass states had exactly the same mass, or if they were all massless, they would all travel through space in exactly the same way. Their quantum waves would stay perfectly in step, perfectly synchronized. The mixture that started as an electron neutrino would remain an electron neutrino forever. Nothing would change. But if the mass states have different masses, even slightly different, they travel at very slightly different speeds. Their quantum waves have very slightly different wavelengths. Over short distances, the difference is negligible. The waves stay nearly synchronized. But over long distances, they gradually drift out of step. The peaks and troughs of one wave slowly shift relative to the peaks and troughs of another. The precise mixture changes. What started as the specific combination corresponding to an electron neutrino gradually morphs into a different combination. And that different combination might correspond to a muon neutrino, or a tau neutrino, or some blend of all 3. The neutrino has oscillated. Its flavor has changed. Think of it like this. Imagine 3 musicians walking side by side, each playing a slightly different rhythm. If they all play at exactly the same tempo, they stay in sync. The combined sound never changes. But if one musician is very slightly faster, the rhythms drift. At first, the difference is barely noticeable, but over time, the patterns shift. Moments that were in harmony become discordant. New patterns emerge. Then the harmony returns, but in a different form. The overall sound oscillates between different combinations as the rhythms cycle in and out of phase. Neutrino oscillation works the same way, except the musicians are quantum waves, the rhythms are wavelengths, and the overall sound is the neutrino's flavor. This is a purely quantum mechanical phenomenon. There is nothing like it in everyday experience. A ball does not change from red to blue as it rolls across the floor. A car does not transform from a sedan into a truck as it drives down the highway. But in the quantum world, particles exist as superpositions of different states, and those superpositions can evolve over time. The evolution depends on the masses of the component states. If the masses are different, the superposition changes. If the masses are all the same or all zero, it does not. Oscillation requires mass differences. Period. No mass differences, no oscillation. This is not an opinion or an interpretation. It is a mathematical consequence of quantum mechanics. The equations are unambiguous. This meant that if neutrino oscillation could be proven to occur, it would automatically prove that neutrinos have mass. The two facts are inseparable. Oscillation equals mass. The question was how to prove it. The solar neutrino problem was suggestive, but it was not proof. Davis's experiment detected only electron neutrinos. If neutrinos were oscillating into other flavors, his experiment would see a deficit. But there could be other explanations. Maybe the solar models were still slightly off. Maybe there was some other unknown process reducing the neutrino flux. To prove oscillation, you needed either to detect the missing flavors directly or to observe the oscillation pattern itself. But there was another layer to the solar neutrino story that made it far richer and stranger than simple vacuum oscillation. In the late 1970s, a physicist at Carnegie Mellon named Lincoln Wolfenstein realized something important. Neutrinos traveling through matter do not oscillate the same way as neutrinos traveling through empty space. Matter changes the oscillation. When a neutrino passes through the dense plasma inside the Sun, it is not moving through a vacuum. It is moving through a sea of electrons, protons, and neutrons packed together at enormous densities. And here is what matters. Electron neutrinos interact with the electrons in that plasma through the weak force. They can scatter off them. Muon neutrinos and tau neutrinos cannot scatter off electrons in the same way, because those interactions require their specific charged lepton partners, which are not present in the solar interior. Only electron neutrinos get this extra interaction. This might sound like a minor detail, but it has an enormous effect. The extra interaction changes the effective mass of the electron neutrino as it travels through dense matter. It is somewhat analogous to how light slows down when passing through glass. The photons are not actually slower. They interact with the atoms in the glass, and those interactions change the effective speed of propagation. Something similar happens to electron neutrinos inside the Sun. The interactions with the solar electrons modify how the neutrino's quantum wave propagates. The effective mass shifts. And because the oscillation pattern depends on the differences between the masses, changing one of them changes the entire oscillation behavior. In the mid-1980s, two Soviet physicists named Stanislav Mikheyev and Alexei Smirnov took Wolfenstein's idea further. They showed that under certain conditions, inside the extraordinarily dense core of the Sun, a remarkable thing can happen. The oscillation is not gradual. It is not a slow drift from one flavor to another over millions of miles. Instead, there can be a resonance, a specific density at which the flavor conversion becomes dramatically enhanced. An electron neutrino produced in the Sun's core, where the density is extremely high, can be almost completely converted into a muon or tau neutrino by the time it exits the Sun, even if the mixing angle in vacuum is relatively small. The dense matter of the Sun amplifies the oscillation enormously. This phenomenon is called the MSW effect, after Mikheyev, Smirnov, and Wolfenstein. It is not speculative. It is a well-understood consequence of quantum mechanics applied to neutrinos traveling through matter, and it has been confirmed by experimental data. The MSW effect explains why the solar neutrino deficit was so large and so consistent. It was not just vacuum oscillation happening over the 93 million miles between the Sun and the Earth. The conversion was happening inside the Sun itself, amplified by the incredible density of the solar core. By the time the neutrinos left the surface of the Sun, most of the electron neutrinos had already been converted into other flavors. The journey through empty space to Earth was almost an afterthought. The damage, from Davis's perspective, was already done before the neutrinos even left the star. This mattered because it changed the predictions. Simple vacuum oscillation would produce a deficit that depends on the distance between the Sun and the Earth, and on the energy of the neutrinos in a specific oscillating pattern. But the MSW effect produces a different signature. It creates a deficit that depends on the neutrino energy in a particular way, determined by the density profile of the solar interior. Higher energy neutrinos, which are produced deeper in the Sun's core where the density is highest, experience the resonance more strongly and are converted more efficiently. Lower energy neutrinos, produced in less dense regions, are converted less. This energy dependence became a crucial diagnostic tool. By measuring the neutrino deficit at different energies, physicists could distinguish between vacuum oscillation and matter-enhanced oscillation, and the data matched the MSW prediction beautifully. The Sun was acting as a natural amplifier for neutrino oscillation, and the pattern it produced carried the fingerprint of the matter effect. The first major breakthrough in directly observing oscillation came from an unexpected direction, not from the Sun, but from the sky above. Cosmic rays, high-energy particles from deep space, constantly bombard Earth's atmosphere. When a cosmic ray proton strikes an atmospheric nucleus high above the ground, it creates a shower of secondary particles. Among these particles are pions, which quickly decay into muons and muon neutrinos. The muons themselves then decay into electrons, electron neutrinos, and more muon neutrinos. The physics of these decays is well understood, and it predicts a specific ratio of muon neutrinos to electron neutrinos arriving at detectors on the ground. For every electron neutrino, there should be about 2 muon neutrinos. In 1998, the Super Kamiokande experiment in Japan announced results that changed everything. Super Kamiokande is a massive detector located in the Kamioka mine in the Japanese Alps, roughly 1,000 meters underground. It consists of a cylindrical stainless steel tank filled with 50,000 tons of ultra-pure water. The walls of the tank are lined with approximately 11,200 photosensitive detectors called photomultiplier tubes. When a neutrino interacts with a water molecule, it can produce a charged particle that travels faster than light travels in water. This is important. Nothing can exceed the speed of light in a vacuum. But light travels slower in water than in a vacuum, about 25% slower. A high-energy charged particle can exceed this reduced speed. When it does, it produces a cone of blue light called Cherenkov radiation, similar to a sonic boom, but with light instead of sound. The photomultiplier tubes detect this faint blue glow and allow physicists to reconstruct the direction and energy of the incoming neutrino. Super Kamiokande studied atmospheric neutrinos, the neutrinos produced by cosmic ray interactions in the atmosphere, and it found something remarkable. Muon neutrinos, coming from directly above the detector, having travelled only about 15 kilometers through the atmosphere, arrived in the expected numbers. But muon neutrinos coming from below, having travelled all the way through the Earth from the atmosphere on the opposite side, roughly 13,000 kilometers, showed a significant deficit. The further the neutrinos travelled, the fewer muon neutrinos arrived. This was the oscillation pattern. Neutrinos travelling short distances had not yet had time to oscillate appreciably. Their quantum waves were still nearly in sync. But neutrinos travelling long distances, thousands of kilometers through the planet, had oscillated significantly. A substantial fraction of the muon neutrinos had transformed into tau neutrinos during the long journey through Earth and were therefore invisible to the detector. The deficit depended on distance travelled, exactly as the oscillation theory predicted. This was not a vague hint. It was a clear, unmistakable signature. Takaaki Kajita, the leader of the Super Kamiokande analysis team, presented these results at the Neutrino Conference in Takayama, Japan, in June of 1998. The evidence was compelling. Atmospheric muon neutrinos were oscillating. They were changing flavour as they travelled, and that meant they had mass. But the solar neutrino problem still needed a definitive resolution. Super Kamiokande had shown oscillation in atmospheric neutrinos. The solar neutrino deficit was almost certainly caused by the same phenomenon, but proving it required a different kind of experiment. You needed a detector that could see all 3 neutrino flavours, not just one. You needed to show that the total number of neutrinos from the Sun matched the predictions, even though the electron-neutrino fraction was low. If the total was right, but the electron fraction was wrong, it would prove the missing electron neutrinos had simply changed flavor, not vanished. This is exactly what the Sudbury Neutrino Observatory did. The SNO detector was located 2 kilometers underground in an active nickel mine near Sudbury, Ontario, in Canada. It consisted of 1,000 tons of heavy water, a special form of water in which the hydrogen atoms are replaced by deuterium, a heavier isotope of hydrogen whose nucleus contains both a proton and a neutron. Heavy water is extraordinarily expensive and rare. The Canadian government loaned roughly $300 million worth of it for the experiment. The heavy water was contained in a spherical acrylic vessel 12 meters in diameter, surrounded by ordinary water and about 9,600 photomultiplier tubes to detect Cherenkov light. Heavy water gave the SNO detector a unique ability. It could detect neutrinos through 3 different reactions, and this is what made the experiment decisive. The first reaction was sensitive only to electron neutrinos. An electron neutrino could interact with a deuterium nucleus and break it apart, turning the neutron into a proton and producing an electron. This reaction, called the charged current reaction, only worked for electron neutrinos because it required the weak force interaction specific to the electron flavor. The second reaction was sensitive to all 3 neutrino flavors equally. Any type of neutrino, electron, muon, or tau, could scatter off a deuterium nucleus and break it apart without changing its own identity. This is called the neutral current reaction, mediated by the Z boson, and it works the same way regardless of the neutrino's flavor. By counting the total number of neutral current interactions, the SNO team could measure the total neutrino flux from the Sun, counting all flavors combined. If the solar models were right and neutrinos were oscillating, the charged current measurement should show a deficit of electron neutrinos, consistent with what Davis had seen for decades. But the neutral current measurement should show the full expected total, because all neutrino flavors would be counted, regardless of which flavor they had oscillated into. In 2001 and 2002, the SNO collaboration published its results. The charged current measurement confirmed the deficit. Roughly 1/3 of the expected electron neutrinos were arriving at the detector, consistent with Davis's original finding. But the neutral current measurement showed the total flux of all neutrino flavors combined was exactly what the solar models predicted. The Sun was producing the right number of neutrinos. The solar models were correct all along. The neutrinos were not disappearing. They were arriving in full force. But 2/3 of them had changed their identity during the trip from the core of the Sun to the detector in Canada. They had oscillated from electron neutrinos into muon and tau neutrinos. The solar neutrino problem, which had haunted physics for over 30 years, was solved. The implications were profound and unambiguous. Neutrinos oscillate. They change flavor. And because oscillation requires different masses for the different mass states, neutrinos must have mass. Not zero mass, actual non-zero mass. This was confirmed, established, settled science. Not speculation, not a hint, not a theoretical possibility. Experimental fact. But science demands independent confirmation, and the most powerful confirmation came not from the Sun or the atmosphere, but from a man-made source: nuclear reactors. In 2002, the same year the SNO collaboration published its landmark results, an experiment in Japan called CAMLAND began collecting data. The name stands for the Kamioka Liquid Scintillator Anti-Neutrino Detector, and it was located in the same Kamioka mine as Super Kamiokande, about 1 kilometer underground. CAMLAND was designed to detect electron antineutrinos produced by nuclear power reactors scattered across Japan. The average distance from the reactors to the detector was roughly 180 kilometers. This distance was carefully chosen. It was the right baseline for neutrino oscillation at the energy scale produced by reactors. Long enough for the oscillation to develop, but short enough that the antineutrino flux was still detectable. Camland used 1,000 tons of liquid scintillator, a transparent oil that produces flashes of light when a charged particle passes through it. When an electron antineutrino interacted with a proton in the scintillator, it produced a positron and a neutron. The positron immediately annihilated with a nearby electron, producing a prompt flash of light. The neutron bounced around for a fraction of a millisecond before being captured by another nucleus, producing a second, delayed flash. This double flash, prompt followed by delayed, was the distinctive signature of an antineutrino interaction. It allowed Camland to distinguish real antineutrino events from background noise with high confidence. The results were striking. Camland detected significantly fewer electron antineutrinos than the reactors were producing. The deficit was consistent with oscillation. But Camland did something more. Because it received antineutrinos at a range of distances from many different reactors, and because the antineutrinos arrived with a spectrum of energies, Camland could actually see the oscillation pattern itself. Not just a deficit, but the characteristic shape of the oscillation, the way the survival probability of electron antineutrinos rises and falls as a function of the ratio of distance to energy. The data showed a clear dip and recovery, a sinusoidal pattern that is the unmistakable fingerprint of quantum mechanical oscillation. It was not merely consistent with oscillation, it was oscillation, directly observed in antineutrinos from a completely artificial source that had nothing to do with the sun or cosmic rays. This was enormously important. The solar neutrino experiments could always be questioned, however unfairly, on the grounds that perhaps the solar models were subtly wrong, or perhaps some unknown solar physics was responsible. The atmospheric neutrino results could be questioned on the grounds that perhaps the cosmic ray flux was not perfectly understood. But nuclear reactors are human-built machines. Their power output is monitored continuously. The number of antineutrinos they produce is calculated from the known physics of nuclear fission with high precision. There was no ambiguity about the source, and Camland saw the oscillation. The reactor antineutrinos were disappearing at exactly the rate and in exactly the pattern predicted by the same oscillation parameters that explained the solar neutrino deficit. Two completely independent sources, the Sun and nuclear reactors, were telling the same story. Neutrinos oscillate. They have mass. The case was closed. In 2015, Takaaki Kajita and Arthur MacDonald were awarded the Nobel Prize in Physics. Kajita for the Super Kamiokande discovery of atmospheric neutrino oscillation, and MacDonald for the SNO measurement proving that solar neutrinos change flavor. The Nobel Committee stated that the discovery had changed our understanding of the innermost workings of matter and could prove crucial to our view of the universe. Ray Davis Jr. had already shared the Nobel Prize in 2002 for his pioneering work on detecting solar neutrinos, the decades of patient measurement that first revealed the deficit. What the oscillation experiments established is worth stating precisely, because the difference between what we know and what remains uncertain matters enormously. We know neutrinos oscillate. This is proven. We know the oscillation requires the three mass states to have different masses. Specifically, we have measured two mass-squared differences, the difference between the squared masses of different pairs of mass states. These measurements are precise and well established. We know the mixing angles, the parameters that describe how the flavor states combine into mass states. 3 mixing angles govern the oscillation pattern, and all 3 have been measured. the last one confirmed in 2012 by the Daya Bay experiment in China. But there are things we do not know. We do not know the absolute masses of the neutrinos. Oscillation experiments measure only differences in the squares of masses, not the masses themselves. We know mass state 2 is heavier than mass state 1, but we do not know whether mass state 3 is the heaviest of the three or the lightest. This is called the mass ordering problem, and it remains one of the major open questions in neutrino physics. We also do not know the exact mass of any individual neutrino mass state. We only know upper limits. The sum of all three neutrino masses is constrained by cosmological observations to be less than roughly 1/5 of an electron volt, but the precise values are unknown. These are staggeringly small numbers. The lightest neutrino might have a mass millionths of times smaller than the electron's mass. There is one more number the oscillation experiments are still chasing, a parameter called the CP violating phase, which describes whether neutrinos and antineutrinos oscillate in exactly the same way or slightly differently. If this parameter is non-zero, it would mean there is a fundamental asymmetry between matter and antimatter in the neutrino sector. This could have deep implications for understanding why the universe contains more matter than antimatter, one of the great unsolved problems in cosmology. Experiments like the ones planned at major neutrino facilities around the world are being designed specifically to measure this parameter. It may take another decade or more to pin it down, but the core discovery is secure. Neutrinos have mass. They oscillate between flavors. These are not hypotheses awaiting confirmation. They are measured, verified, Nobel Prize-winning facts. And they break the standard model. Not by contradicting its successful predictions, but by revealing something it never accounted for. The simplest version of the standard model has no room for neutrino mass. Every attempt to include it requires adding something new, something that was not in the original theory. The crack is confirmed. The question now is what lies behind it. That is where the real trouble begins, because fitting neutrino mass into the standard model is not as simple as adjusting a number or adding a small correction. The problem goes much deeper. The Higgs mechanism, the beautiful machinery that gives every other particle its mass, does not work for neutrinos without fundamental modifications. Something about neutrinos is different. Something about the way they acquire mass, if they acquire it the same way at all, points to physics that the standard model was never designed to describe. Now we arrive at the heart of the problem. Neutrinos have mass. The experiments have settled that beyond any doubt. But why is that a problem? Why can the standard model not simply absorb this fact and move on? After all, every other matter particle in the theory has mass. Electrons have mass. Quarks have mass. Even the muon and the tau have mass. So why is it so difficult to give mass to the neutrino? The answer has to do with how mass works in the standard model. Mass is not something that particles simply have as a built-in, inherent property. In the standard model, mass is something particles acquire through a specific mechanism, and that mechanism has rules. It has requirements. It demands certain ingredients. And for neutrinos, those ingredients are missing. To understand why, we need to look carefully at how the Higgs mechanism actually gives particles their mass. Because once you see how it works for every other particle, you will see exactly why it breaks down for neutrinos. In the 1960s, physicists faced a serious theoretical problem. The equations of the standard model, specifically the equations describing the weak force, only worked correctly if the W and Z bosons were massless. But the W and Z bosons are not massless. They are extremely heavy, roughly 85 and 97 times the mass of a proton. If you simply wrote their masses into the equations by hand, the mathematics fell apart. The theory produced infinite answers for processes that should give finite, physical results. Something was deeply wrong. The solution came from the Higgs mechanism, developed independently by several physicists in 1964. The idea is that empty space is not really empty. It is filled with a field called the Higgs field, and this field has a non-zero value everywhere in the universe. It is not zero in empty space. It has a constant, uniform value that permeates all of existence. When certain particles move through this field, they interact with it, and that interaction slows them down, gives them inertia, gives them what we experience as mass. Different particles interact with the Higgs field with different strengths, which is why different particles have different masses. The top quark interacts very strongly with the Higgs field, so it has a large mass. The electron interacts weakly with the Higgs field, so it has a small mass. A photon does not interact with the Higgs field at all, so it remains massless and travels at the speed of light. This is an elegant solution. Instead of putting masses into the equations by hand and breaking the mathematics, you introduce a field that generates masses dynamically. The equations remain well behaved, the infinities cancel, the theory makes sense. And the Higgs boson, the quantum excitation of the Higgs field, was eventually discovered at CERN in 2012, confirming that the mechanism is real. But the Higgs mechanism does not work for free. It has a specific requirement. To generate mass for a fermion, a matter particle, through the Higgs mechanism, you need that particle to exist in two forms. These two forms are called left-handed and right-handed, and they refer to a quantum property called chirality. This is not about the particle physically spinning clockwise or counterclockwise like a top. Chirality is an intrinsic quantum property that describes how a particle transforms under certain mathematical symmetry operations. It determines how the particle interacts with the weak force. Left-handed particles and right-handed particles behave very differently under the weak force. In fact, one of the most striking features of the Standard Model is that the weak force only affects left-handed particles. It completely ignores right-handed particles. A left-handed electron can interact with a W boson or a Z boson. A right-handed electron cannot. This asymmetry between left and right is deeply built into the theory. It is not a minor detail. It is fundamental to how the weak force operates. Now, here is the critical point about how the Higgs mechanism generates mass. The Higgs field does not interact with a left-handed particle and give it mass directly. What the Higgs field does is connect the left-handed version of a particle to the right-handed version. It creates a coupling between the two. This coupling is what we experience as mass. A massive particle is constantly flipping between its left-handed and right-handed forms, mediated by the Higgs field. It oscillates back and forth, left to left to right, and this constant flipping is what makes the particle behave as though it has inertia, as though it has mass. Think of it roughly like this. Imagine walking through a crowded room. If you can move freely, you move fast. That is like being massless. But now imagine the crowd keeps turning you around. You take a step forward, someone turns you around, you step the other way, someone turns you again. Your progress slows. You have effective inertia. The Higgs field does something analogous. It keeps flipping the particle between its left-handed and right-handed states, and this constant flipping gives the particle mass. The stronger the coupling between the two states, the more mass the particle has. For the electron, this works beautifully. The Standard Model contains both a left-handed electron and a right-handed electron. The Higgs field couples them together. The coupling constant, called a Yukawa coupling, determines the electron's mass. For quarks, the same thing works. Every quark exists in both a left-handed and a right-handed version. The Higgs field couples the two. Different quarks have different Yukawa couplings, which is why they have different masses. The mechanism is the same for every fermion in the Standard Model. Left-handed version, right-handed version, Higgs coupling between them. Mass generated. Mathematics consistent. Everything works. Except for neutrinos. In the original Standard Model, there is no right-handed neutrino. It does not appear in the theory. It is not listed among the particles. It was never observed in any experiment. And there was a good reason for this omission. The right-handed neutrino, if it existed, would be the most invisible particle imaginable. A right-handed neutrino would carry no electric charge, so electromagnetism ignores it. It would not be a quark, so the strong force ignores it. And because the weak force only affects left-handed particles, even the weak force would ignore a right-handed neutrino. A right-handed neutrino would interact with nothing. It would feel no force at all within the Standard Model framework. It would be a particle that cannot be produced or detected through any known interaction. It would be a ghost among ghosts. Because there was no experimental evidence for such a particle, and no theoretical need for it if neutrinos were massless, the Standard Model simply left it out. The theory was built with only left-handed neutrinos, and with only a left-handed version available, the Higgs mechanism could not generate neutrino mass. There was nothing for the Higgs field to couple the left-handed neutrino to. One half of the machinery was missing. It is as if you had one end of a bridge but no other end to connect it to. The bridge cannot be built. The mass cannot be generated. This is why neutrino mass breaks the Standard Model. It is not that the Standard Model predicts the wrong mass for the neutrino. It is that the Standard Model, in its simplest form, has no way to give neutrinos mass at all. The mechanism that works for every other particle simply does not apply. To accommodate neutrino mass, you must add something new to the theory, something that was not there before. And the moment you add something new, you are no longer working within the Standard Model. You have gone beyond it. So what can you add? Physicists have proposed two fundamentally different ways to give neutrinos mass, and they lead to very different pictures of what neutrinos actually are. Both approaches work mathematically. Both are consistent with current experiments, but they imply profoundly different things about the nature of these particles and about the physics that lies beyond the Standard Model. The first approach is the most straightforward. You simply add a right-handed neutrino to the Standard Model. You put the missing piece into the theory. Once you have both a left-handed and a right-handed neutrino, the Higgs mechanism can couple them together in exactly the same way it couples left-handed and right-handed electrons or quarks. The neutrino acquires mass through a U-Kawar coupling to the Higgs field, just like every other fermion. This type of mass is called Dirac mass, named after the physicist Paul Dirac, who first wrote down the equation describing massive fermions in the late 1920s. In some ways, this is the simplest solution. You are not changing the mechanism. You are not inventing new physics. You are just adding a particle that was left out. The machinery already exists. You are just providing the missing part. But this solution creates its own problem, a massive problem, in fact. If neutrino mass arises through the Higgs mechanism with a U-Kawar coupling, then the U-Kawar coupling of the neutrino must be extraordinarily, absurdly small. The U-Kawar coupling is directly proportional to the particle's mass. The top quark has the largest U-Kawar coupling, roughly 1, corresponding to its huge mass of about 173 giga-electron-volts. The electron has a U-Kawar coupling of about 3 millionths. That already seems small. But the neutrino, with a mass of less than 1 electron-volt, would need a U-Kawar coupling of roughly 10 to the negative 12th power or smaller, about 1,000,000 times smaller than even the electron's tiny coupling, and a full 1,000,000,000,000 times smaller than the top quarks. 12 orders of magnitude below the strongest Yukawa coupling in the theory. There is no known reason for such a tiny number. Nothing in the Standard Model explains why one particle's coupling to the Higgs field should be 1 trillion times smaller than another's. Every other fermion's Yukawa coupling falls within a range spanning about 5 or 6 orders of magnitude, from the electron to the top quark. That range is already considered uncomfortably wide, and physicists have long wondered why it exists. But the neutrino's coupling would extend that range by another 6 or more orders of magnitude. It would be a staggering outlier, an inexplicable number dropped into the theory without explanation. Physicists do not like inexplicable numbers. They are almost always signs that something deeper is going on, that the real explanation lies beyond the current theory. Furthermore, the right-handed neutrino you would need to add is unlike any other particle in the Standard Model. Every other particle in the theory interacts through at least one force. Even the neutrino's left-handed version interacts through the weak force. But the right-handed neutrino, as we discussed, would interact through nothing. It is completely sterile. It has no charge of any kind that any Standard Model force can see. This makes it unique. It sits in the theory doing absolutely nothing, except providing a partner for the Higgs mechanism to couple to. It is not clear why nature would include such a particle. It is not clear how you would ever detect it. You would be adding a particle to the theory that is in principle invisible, and whose only purpose is to solve the mass problem. It works, but it feels unsatisfying. It feels like you are papering over a crack rather than understanding what caused it. The second approach is more radical, and it leads to one of the most fascinating possibilities in all of particle physics. In 1937, the Italian physicist Ettore Majorana proposed that neutrinos might be a special type of particle, fundamentally different from every other fermion. Every other matter particle we know has a distinct antiparticle. The electron has the positron, each quark has an antiquark, the muon has the anti-muon. A particle and its antiparticle have opposite charges but otherwise identical properties. They are distinct. They are not the same thing. Majorana proposed that the neutrino might be its own antiparticle. A Majorana neutrino and a Majorana antineutrino would be the same particle. Not just similar, identical. The same physical entity. This might seem like a minor distinction, but it has enormous consequences. If neutrinos are their own antiparticles, they can acquire mass through a completely different mechanism, one that does not require the Higgs field at all, and does not require a right-handed partner in the usual sense. A Majorana mass term connects a left-handed neutrino directly to itself, or, more precisely, to the charge conjugate of itself, which is mathematically equivalent to a right-handed antineutrino. If the neutrino is its own antiparticle, then the charge conjugate of a left-handed neutrino is itself a right-handed neutrino. The particle provides its own partner. The bridge connects back to itself. Mass can be generated without adding a new particle. But this comes with its own cost. A Majorana mass term violates a quantity called lepton number. In the Standard Model, there is a conservation law that says the total number of leptons minus the total number of antileptons is conserved in every interaction. An electron neutrino is always produced alongside a positron, or absorbed alongside an electron, preserving lepton number. Majorana mass violates this conservation law. If a neutrino is its own antiparticle, then the distinction between lepton and antilepton becomes blurred for neutrinos, and lepton number is no longer strictly conserved. This is a departure from the Standard Model. It means a symmetry that was previously exact becomes only approximate, broken by the Majorana mass. This might sound troubling, but many physicists actually find it appealing. Lepton number conservation was never deeply justified within the Standard Model. It is what physicists call an accidental symmetry. It falls out of the equations, but there is no deep principle requiring it. Many theories that go beyond the standard model naturally predict that lepton number is violated. Finding that neutrinos are mi or ana particles would be evidence for these larger theories. Now here is where the two approaches combine into something truly elegant. The most compelling theoretical framework for explaining neutrino mass uses both Dirac mass and mi or ana mass simultaneously. This framework is called the seesaw mechanism, and it is one of the most beautiful ideas in theoretical particle physics. It explains not just that neutrinos have mass, but why their mass is so incomprehensibly tiny compared to every other particle. The seesaw mechanism starts by assuming right-handed neutrinos do exist, but that they are extremely heavy. Not light like the neutrinos we observe, but massive. Possibly as heavy as 10 to the 15th giga-electron volts, approaching the energy scale where the strong, weak, and electromagnetic forces might unify into a single force. This is called the Grand Unified Theory scale. These right-handed neutrinos are far too heavy to produce in any current or foreseeable experiment. They would have existed in the extreme conditions of the very early universe and decayed long ago. In the seesaw mechanism, there are two types of mass at play. There is a Dirac mass connecting the left-handed and right-handed neutrinos through the Higgs field, similar in size to the masses of other fermions. And there is a mi or ana mass, which applies only to the right-handed neutrinos and is enormously large. These two masses interact through the equations, and the result is a mathematical seesaw. When one side is heavy, the other side is forced to be light. The heavier the right-handed neutrino, the lighter the left-handed neutrino. The relationship is inverse. If the right-handed neutrino has a mass near the Grand Unified Theory scale, and the Dirac mass is similar to a typical fermion mass, the resulting light neutrino mass comes out naturally in the range of a fraction of an electron volt, exactly where we observe it. This is remarkable. The seesaw mechanism does not need to assume the neutrino's Yukawa coupling is absurdly tiny. The coupling can be perfectly reasonable, similar to the couplings of other particles. The tiny observed neutrino mass is not the result of a tiny coupling. It is the result of a mathematical suppression caused by the enormous mass of the right-handed neutrino. The lightness of the neutrinos we observe is a consequence of the heaviness of particles we cannot see. A normal-sized number divided by a very large number gives a very small number. That is the seesaw. That is why it works. Let me put some rough numbers on this to show you how naturally it falls out. Suppose the right-handed neutrino has a Majorana mass of about 10 to the 15th giga-electron volts. That is approximately the Grand Unified Theory scale. And suppose the Dirac mass generated by the Higgs mechanism is about 100 giga-electron volts, roughly the mass of the top quark. The seesaw formula gives the light neutrino mass as roughly the Dirac mass squared divided by the Majorana mass. That comes out to about 100 squared divided by 10 to the 15th, which is 10,000 divided by 10 to the 15th, which is 10 to the negative 11 giga-electron volts. Converting to electron volts, that is about 1/100th of an electron volt. That is precisely the ballpark of the neutrino masses inferred from oscillation experiments. The mechanism gives the right answer without any fine-tuning, without any absurdly small numbers, without any arbitrary adjustments. The answer falls out naturally from the mathematics. This is why so many physicists find the seesaw mechanism compelling. It does not just accommodate neutrino mass, it explains the smallness of neutrino mass. It connects the neutrino mass scale to an entirely different energy scale, the Grand Unified Theory scale, where the fundamental forces might unify. It predicts that neutrinos are Majorana particles. It predicts that lepton number is violated. and it suggests that there exist extremely heavy right-handed neutrinos that played a role in the early universe. In fact, the seesaw mechanism may even help explain one of the greatest mysteries in cosmology. Why does the universe contain more matter than antimatter? The Big Bang should have produced equal amounts of matter and antimatter, yet the universe we observe is overwhelmingly made of matter. Every atom in your body, every star you see, every galaxy telescopes have ever recorded, all matter. The antimatter is gone. Something in the early universe must have created a tiny imbalance, a slight excess of matter over antimatter, and that excess is everything we see today. One of the leading explanations for this asymmetry is a process called leptogenesis. In leptogenesis, the extremely heavy right-handed neutrinos predicted by the seesaw mechanism decay in the very early universe. Because these decays violate lepton number, and because the conditions in the early universe are far from equilibrium, the decays can produce slightly more leptons than antileptons. This lepton asymmetry is then partially converted into a baryon asymmetry, an excess of protons and neutrons over antiprotons and antineutrons, through processes in the standard model called sphaleron transitions. The result is a universe with slightly more matter than antimatter, exactly what we observe. This is speculative. Leptogenesis has not been proven. We cannot recreate the conditions of the early universe in a laboratory. We cannot produce or observe the heavy right-handed neutrinos directly, but the framework is internally consistent, mathematically rigorous, and connects the neutrino mass puzzle to the matter-antimatter asymmetry of the universe. Two seemingly unrelated mysteries potentially explained by the same physics. But we must be careful. The seesaw mechanism, for all its elegance, is a theoretical framework. It has not been experimentally confirmed. We do not know whether right-handed neutrinos exist. We do not know whether they are heavy or light. We do not know whether neutrinos are mi or ana particles. These are open questions, the subject of active experimental and theoretical research. The seesaw mechanism is the leading candidate explanation, but it is not the only one. Other mechanisms exist that can generate small neutrino masses through different physics. Some invoke extra dimensions. Some invoke new symmetries. Some invoke radiative corrections, where neutrino mass arises not at the fundamental level, but as a quantum effect from loops of virtual particles. Each approach has its own predictions and its own implications for what lies beyond the standard model. What is certain, what is not speculative, is that the standard model in its original form cannot explain neutrino mass. Every solution requires new physics. Whether it is a right-handed neutrino, a mi or ana mass term, a seesaw mechanism, extra dimensions, or something else entirely, you must add something to the theory. The standard model alone is not enough. The crack is real, and it runs deeper than a simple missing number. It suggests entirely new particles, new symmetries, new energy scales, and possibly new principles of nature that we have not yet discovered. The Higgs boson discovery completed the standard model in one sense. Every particle the theory predicted has been found. Every measurement confirms its equations to extraordinary precision. But the neutrino mass problem shows that completion is not the same as perfection. The standard model is complete in the sense that all its predicted particles exist. It is incomplete in the sense that it cannot account for something nature clearly does. Neutrinos have mass. The theory says they should not. That tension, that gap between what the theory describes and what nature demands, is the crack. And the question that drives a generation of physicists is what lies on the other side of it. Everything we have discussed so far, the oscillation experiments, the mass problem, the seesaw mechanism, all of it rests on our ability to detect a particle that does everything in its power to avoid being detected. And that is perhaps the most remarkable part of this entire story. Neutrinos are, by any practical measure, the closest thing nature has to invisible. They carry no electric charge. They do not feel the strong force. The only force in the standard model that can touch them is the weak force, and the weak force earns its name. The probability that any individual neutrino will interact with any individual atom is so vanishingly small that it borders on the absurd. And yet physicists have built machines capable of catching them. Enormous machines. Machines buried deep underground, filled with thousands of tons of water or liquid or ice, instrumented with thousands of ultra-sensitive light detectors, operated for years or decades at a time, all to capture a handful of interactions from a flood of trillions upon trillions of particles that would otherwise pass through without a trace. The reason neutrino experiments must be so large is pure statistics. If the probability of any single neutrino interacting is extraordinarily low, then the only way to see a meaningful number of interactions is to put an enormous number of target atoms in the path of an enormous number of neutrinos and wait. You are playing a game of chance with terrible odds, and your only strategy is volume and patience. More target material means more atoms for the neutrinos to potentially interact with. More neutrinos means more chances. More time means more accumulated events. Everything about neutrino detection is a battle against improbability. Consider the scale involved. The Super Kamiokande detector in Japan contains 50,000 tons of ultra-pure water. That is roughly enough water to fill 20 Olympic swimming pools. The water must be extraordinarily pure because even trace amounts of radioactive contaminants would produce signals that mimic neutrino interactions, drowning out the real events in a sea of false alarms. The detector sits 1,000 meters underground in an old zinc mine. The kilometer of rock overhead acts as a shield, filtering out the cosmic rays that constantly bombard Earth's surface. Only neutrinos, which pass through rock effortlessly, can reach the detector from above. And muons, which are created by cosmic rays in the atmosphere and are energetic enough to penetrate deep underground, must also be carefully accounted for and subtracted from the data. Even with 50,000 tons of water and a powerful source of neutrinos, the detection rate is modest. When Super Kamiokande studies atmospheric neutrinos, it detects roughly 10 interactions per day. 10 events. Out of the billions of neutrinos passing through the detector every second, about 10 per day actually interact with a water molecule and produce a detectable signal. That ratio, 10 detections out of billions upon billions of opportunities, gives you a sense of just how ghostly these particles truly are. The IceCube Neutrino Observatory at the South Pole takes a different approach entirely. Rather than building a tank and filling it with water, the IceCube collaboration used the Antarctic ice sheet itself as the detector. They drilled 86 holes into the ice, each about 2.5 kilometers deep, and lowered strings of digital optical sensors into them. In total, more than 5,000 light sensors are embedded in a cubic kilometer of ice. That is 1 billion tons of frozen water instrumented to detect the faint flashes of Cherenkov light produced when a high-energy neutrino interacts with an atom in the ice. IceCube is the largest neutrino detector ever built, and it primarily studies high-energy neutrinos from cosmic sources, exploding stars, active galaxies, and other violent astrophysical events. Even with 1 billion tons of ice, IceCube detects only about one high-energy cosmic neutrino per month that is clearly distinguishable from the background of atmospheric neutrinos. These experiments are engineering marvels, pushed to the limits of what is technically achievable. The photomultiplier tubes used in water Cherenkov detectors like Super Kamiokande can detect a single photon of light. 1 photon. The detectors are so sensitive that they can reconstruct the direction and energy of an incoming neutrino from the faint cone of blue light produced when the neutrino's interaction creates a fast-moving, charged particle. The data analysis requires years of careful work, sifting through millions of recorded events, rejecting backgrounds, calibrating the detector response, and extracting the tiny signal buried in the noise. And all of this effort, all of this technology, all of this patience has produced some of the most important discoveries in the history of physics. The confirmation of neutrino oscillation. The proof that neutrinos have mass. Evidence that the standard model is incomplete. The fact that these discoveries came from particles so elusive they can pass through a planet without stopping makes them all the more extraordinary. There is something worth pausing on here. Something about the sheer human scale of what neutrino physics demands. These experiments are not the work of a single brilliant mind working alone at a desk. They are the work of thousands of people. Hundreds of physicists, engineers, technicians, graduate students and support staff spread across dozens of institutions in multiple countries, collaborating for decades on a single measurement. The SNO experiment relied on 1,000 tons of borrowed heavy water, worth more than most particle physics detectors themselves. The Dune experiment requires excavating 800,000 tons of rock from the Sanford Underground Research Facility in South Dakota to create caverns large enough to hold 70,000 tons of liquid argon, a volume of cryogenic fluid larger than anything ever contained underground. The logistics alone are staggering before a single neutrino is detected, and the timescales are immense. Ray Davis Jr. began his experiment in the Homestake mine in 1965. He published his first results in 1968. The definitive resolution of the problem he uncovered did not come until 2001, when the SNO results were announced. That is 36 years from the start of the experiment to the answer. Davis spent the most productive decades of his career measuring a deficit that most of the physics community believed was a mistake. He endured skepticism, doubt, and occasional dismissal. He kept running his experiment, kept extracting argon atoms, kept reporting the same stubborn one-third deficit year after year, decade after decade, trusting his work against the weight of collective opinion. He was ultimately vindicated, awarded the Nobel Prize in 2002 at the age of 88. He died 4 years later. The universe had forced physics to wait for a generation before it revealed what his experiment had been telling them all along. That kind of patience is not unique to Davis. It is built into the fabric of neutrino physics. The Dune experiment was formally proposed in the early 2010s. First beam is not expected until the late 2020s at the earliest, and the experiment will run for decades after that. The physicists who conceived the experiment may well retire before its most important results are published. Some of the graduate students who helped build the detector will become professors, mentor their own students, and see those students graduate before Dune completes its primary mission. This is science on a timescale that exceeds individual careers. Science where you may contribute a critical piece of the puzzle, knowing you will not live to see the final picture. And the environments in which this work happens are extraordinary in their own right. Neutrino physicists work underground. Not in the metaphorical sense, literally underground, in mines and tunnels, sometimes a mile or more below the surface. They descend in cage elevators or drive down long, spiraling access tunnels carved from rock. They work in caverns that are kept meticulously clean, sealed off from the dust and radon that seep from surrounding stone. The air is filtered, the materials are screened. Even the concrete used to line the cavern walls is specially formulated to minimize radioactive contamination from naturally occurring uranium and thorium. These are among the cleanest, quietest environments on the planet, built not for human comfort, but for the faintest possible whisper of a particle interaction. The scientists who work in these environments spend weeks underground during installation and calibration phases. They eat their meals underground, they troubleshoot equipment underground, and when the detector is running, many of them are thousands of miles away, analyzing data that streams in from sensors buried in rock or ice. looking for the barely perceptible traces of particles that pass through the Earth without caring that anyone is watching. This is what it takes to study neutrinos. This is the price of listening to the universe's quietest voice. And the fact that humanity is willing to pay this price, willing to build billion-dollar detectors underground and operate them for decades to catch a handful of events per day from a particle that barely exists by ordinary standards, says something important about what drives us. Not every question has a practical payoff. Not every discovery leads to a new technology. But the need to know, the need to understand the rules that govern reality at its deepest level, that is a human impulse that has driven science for centuries and shows no sign of diminishing. Now let us turn to the questions that remain open. Because while we know neutrinos have mass and we know they oscillate, there is an enormous amount we still do not know. The oscillation experiments have measured the differences between the squared masses of the three mass states with good precision. But they have not told us the absolute masses. They have not told us the ordering. And they have not told us whether neutrinos are their own antiparticles. Each of these unanswered questions has the potential to reshape our understanding of particle physics and cosmology. The mass ordering problem is one of the most pressing. We know there are three neutrino mass states. We know mass state 2 is heavier than mass state 1. The squared mass difference between them has been measured from solar neutrino oscillations. We also know the squared mass difference between mass state 3 and the other two, measured from atmospheric neutrino oscillations. This second difference is much larger. But we do not know whether mass state 3 is the heaviest of the three or the lightest. If mass state 3 is the heaviest, the ordering goes 1, 2, 3, from lightest to heaviest. Physicists call this the normal ordering because it mirrors how the charged leptons are arranged. The electron is lightest, the muon is heavier, and the tau is heaviest. If neutrino masses follow the same pattern, it would suggest a deep structural similarity between the mass hierarchies of charged and neutral leptons. But mass state 3 could also be the lightest, with mass states 1 and 2 being heavier. This is called the inverted ordering. In this scenario, two mass states are relatively heavy and close together, with a lighter one below them. The inverted ordering would be unusual. It would break the pattern seen in the charged leptons and suggest something unexpected about how neutrino masses are generated. The mass ordering matters because it has consequences for other measurements and for theoretical models. Different orderings lead to different predictions for the rate of neutrinoless double beta decay, which we will discuss shortly. Different orderings affect how neutrinos propagate through matter, which changes the oscillation patterns observed in long baseline experiments. And different theoretical models of neutrino mass, different versions of the seesaw mechanism, different grand unified theories, often predict one ordering or the other. Determining the ordering experimentally would immediately rule out a large class of theories and constrain the physics beyond the standard model. Several experiments are being built or are already running to resolve this question. The Juno experiment, short for the Jiangmen Underground Neutrino Observatory, is being constructed in southern China. It is a 20,000-ton liquid scintillator detector located about 700 meters underground and positioned roughly 53 kilometers from two powerful nuclear reactor complexes. Reactor antineutrinos will travel 53 kilometers to the detector, oscillating along the way. The oscillation pattern at this specific distance is sensitive to the mass ordering. By measuring the energy spectrum of arriving antineutrinos with extraordinary precision, Juno aims to determine whether the normal or inverted ordering is correct. The experiment is expected to start collecting data in the coming years. The Dune experiment, the Deep Underground Neutrino experiment, takes a different approach. It will use a powerful neutrino beam generated at Fermilab in Illinois and aim it at massive detectors located 1,300 kilometers away in South Dakota, deep underground in the Sanford Underground Research Facility. The neutrinos will travel through the Earth's mantle on their journey from Illinois to South Dakota. As they pass through matter, their oscillation is modified in a way that depends on the mass ordering. By comparing the oscillation patterns of neutrinos and antineutrinos over this enormous baseline, DUNE will be sensitive to the ordering. DUNE is also designed to measure the CP violating phase, the parameter that describes whether neutrinos and antineutrinos oscillate differently. This measurement could have profound implications for understanding why the universe contains more matter than antimatter. Then there is the question of absolute neutrino mass. Oscillation experiments tell us only the differences between squared masses, not the masses themselves. The lightest neutrino could have a mass very close to zero, with the others slightly heavier. Or all three could have masses that are relatively similar, much larger than the differences between them. The absolute mass scale matters for cosmology, because neutrinos are so abundant that even a tiny mass per neutrino adds up to a significant fraction of the total mass in the universe. The Katrine experiment in Germany is the most direct attempt to measure neutrino mass. Katrine studies the beta decay of tritium, a radioactive isotope of hydrogen. When tritium decays, it emits an electron and an electron antineutrino. The electron carries away most of the energy, but the neutrino carries away some. By measuring the electron's energy with extreme precision, right at the maximum possible energy where the neutrino carries away almost nothing, physicists can infer the neutrino's mass. If the neutrino has mass, there will be a tiny deficit of electrons at the highest energies, because some energy must go into creating the neutrino's rest mass. Katrine uses a massive spectrometer, about 24 meters long and 10 meters in diameter, to measure electron energies with a precision of better than 1 electron volt. It is one of the most precise spectrometers ever built. As of its latest results, Katrine has set an upper limit on the electron-neutrino mass of about 45 hundredths of an electron volt. This is the tightest direct laboratory limit ever achieved. Future runs may push this limit lower or potentially detect a non-zero mass directly. If the neutrino mass is in the range of a few tenths of an electron volt, Katrine has a chance of measuring it. If it is much smaller, we may need a next-generation experiment. Cosmological observations provide complementary constraints. The cosmic microwave background radiation and the large-scale distribution of galaxies are both sensitive to the total mass of all three neutrino species combined. Neutrinos were abundant in the early universe, and their mass affects how structures like galaxies and galaxy clusters formed. Heavier neutrinos suppress the formation of small-scale structures because they move fast enough to smooth out density fluctuations. By comparing the observed distribution of galaxies with theoretical predictions, cosmologists can set upper limits on the sum of neutrino masses. Current limits from cosmological data are roughly comparable to the Katrine limit, but approach it from a completely different direction, providing independent confirmation. Perhaps the most profound open question is whether neutrinos are me or ana particles. Are they their own antiparticles? This question goes to the heart of what neutrinos are and what physics lies beyond the standard model. If neutrinos are me or ana particles, it would confirm that lepton number is not a fundamental symmetry of nature. It would strongly support the seesaw mechanism. It would have implications for leptogenesis and the origin of the matter-antimatter asymmetry. It would mean that neutrinos are fundamentally different from every other known fermion. There is only one known way to test this experimentally. It is called neutrinoless double beta decay, and searching for it is one of the highest priorities in particle physics today. Normal double beta decay is a rare but known process in which two neutrons in a nucleus simultaneously decay into two protons, emitting two electrons and two antineutrinos. This process has been observed in several isotopes. It is slow, with half-lives of 10 to the 19th years or longer, but it is consistent with the standard model. Neutrinoless double beta decay would be different. In this hypothetical process, the two neutrons still decay, and two electrons are still emitted, but no neutrinos come out. The antineutrino emitted by one decaying neutron is absorbed by the other decaying neutron as if it were a neutrino. This is only possible if the neutrino and the antineutrino are the same particle. If the neutrino is its own antiparticle. If it is a Majorana particle. In neutrinoless double beta decay, all the energy goes into the two electrons and the recoiling nucleus. No energy is carried away by invisible neutrinos. This means the two electrons carry a specific, fixed total energy equal to the full energy released in the decay. In normal double beta decay, the energy is shared among the electrons and the neutrinos, so the electron energies vary from event to event. The signature of the neutrinoless process is a sharp spike in the combined electron energy spectrum at exactly the transition energy, a peak that should not be there if neutrinos are DIH-RAC particles. Finding this peak would be monumental. It would prove neutrinos are Majorana particles. It would prove lepton number is violated. It would provide information about the absolute neutrino mass scale, because the rate of neutrinoless double beta decay depends on a quantity called the effective Majorana mass. It would open a window onto physics at energy scales far beyond the reach of any accelerator. But searching for this process is extraordinarily difficult. The expected half-life for neutrinoless double beta decay, if it occurs at all, is immensely long. Current limits push it beyond 10 to the 26th years for certain isotopes. That is roughly 1,000,000 billion times longer than the age of the universe. To have any hope of seeing it, you need enormous quantities of the decaying isotope, extremely low background noise, and exquisite energy resolution to identify the sharp peak above any residual background. Several experiments around the world are pursuing this search. They use different isotopes, xenon-136, germanium-76, and others, and different detection technologies. The experiments are located deep underground to shield against cosmic rays. The materials used in construction are selected for extreme radio purity, screened for even trace amounts of natural radioactivity. Every component is tested, every surface is cleaned. The environments are among the most pristine and quiet on Earth, engineered specifically to reduce noise to the absolute minimum, so that a handful of events, perhaps a few per year in a ton of material, might be detected above the background. No experiment has yet observed neutrinoless double beta decay. The current limits tell us that if the process occurs, it is extremely rare. But the sensitivity is improving with each generation of experiments. Within the next decade, a new wave of experiments will probe the parameter space predicted by the inverted mass ordering scenario. If neutrinos have the inverted ordering and are Majorana particles, these next-generation experiments have a realistic chance of seeing the signal. If the ordering is normal, the signal may be too faint for current technology, and we will need yet another generation of even larger, even quieter experiments. There is also the question of CP violation in the neutrino sector. CP symmetry relates particles to their antiparticles and reflects their spatial coordinates. If CP symmetry holds for neutrinos, then neutrinos and antineutrinos oscillate in exactly the same way. If it is violated, they oscillate differently. The amount of violation is parameterized by a phase angle, and measuring that angle is one of the primary goals of the DUNE experiment and the Hyper Kamiokande experiment in Japan, which is the successor to Super Kamiokande with a detector 8 times larger. CP violation in the neutrino sector could be connected to the origin of the matter-antimatter asymmetry through leptogenesis, as we discussed earlier. If the CP violation measured at low energies in neutrino oscillation experiments is related to the CP violation that occurred at extremely high energies in the early universe, it would provide evidence for leptogenesis and link neutrino physics to the largest scale structure of the cosmos. The connection between the two is not direct. The CP violation in oscillation experiments and the CP violation in leptogenesis involve different parameters in general, but in certain theoretical models they are related, and measuring one constrains the other. Let us step back now and consider the full picture. What have neutrinos taught us, and why should anyone who is not a particle physicist care? The Standard Model of particle physics is one of humanity's greatest intellectual achievements. It describes the fundamental constituents of matter and the forces that govern their behavior with extraordinary precision. It has been tested and confirmed thousands of times over half a century. It predicted the existence of particles that were later discovered. It calculated quantities that were later measured to astonishing accuracy. By almost any standard, it is a triumph of human understanding. And yet, it is wrong. Not badly wrong, not wildly wrong, but wrong in a way that matters enormously. Neutrinos have mass, and the Standard Model, in its simplest and most elegant form, cannot account for that mass. This is not a rounding error. This is not an approximation breaking down at the margins. This is a qualitative failure. The theory lacks the ingredients to explain something that nature clearly does. Every solution to the neutrino mass problem requires adding something new to the theory, something that was not there before. A right-handed neutrino, a Majorana mass term, a seesaw mechanism, new symmetries, new energy scales, new particles. The details differ from model to model, but the conclusion is universal. The Standard Model is incomplete. It is not the final theory. There is more to discover. And neutrinos are the signpost pointing the way. They are the only confirmed evidence we have, the only experimentally established fact that definitively requires physics beyond the Standard Model's simplest structure. Dark matter is strong evidence that something is missing, but we have not identified what dark matter is made of. Dark energy is deeply mysterious, but it lives in the realm of cosmology and general relativity, somewhat outside the Standard Model's jurisdiction. The hierarchy problem, the puzzle of why the Higgs boson mass is so much lighter than the Planck scale, is a theoretical concern, not an experimental measurement that contradicts the theory. Neutrino mass is different. It is a measured fact. Neutrinos oscillate. This has been observed in solar neutrinos, atmospheric neutrinos, reactor neutrinos, and accelerator neutrinos. Multiple independent experiments using different sources and different detection techniques all agree. The oscillation is real. The mass is real. And the Standard Model cannot explain it. This makes neutrinos the one confirmed crack in the most successful theory in the history of science. That crack might be small. The neutrino masses are tiny, far smaller than any other fermion mass. The effects are subtle, detectable only in enormous experiments after years of patient observation. From the outside, it might seem like a minor issue, a small imperfection in an otherwise flawless theory. But in physics, small cracks can open onto vast new landscapes. The tiny discrepancy in Mercury's orbit that Newtonian gravity could not explain led to general relativity and a complete reimagining of space and time. The ultraviolet catastrophe, a seemingly minor failure of classical physics to describe the radiation emitted by hot objects, led to quantum mechanics and a revolution in our understanding of nature at the smallest scales. Small cracks have a way of revealing enormous depths. The neutrino mass problem might be exactly this kind of crack. It might be the first visible sign of an entirely new layer of physics, a layer that includes new particles, new forces, new symmetries, and new principles that we have not yet discovered. The seesaw mechanism hints at physics at the grand unified theory scale, energies 1 trillion times higher than anything we can produce in a laboratory. Majorana neutrinos hint at the violation of lepton number and the origin of matter itself. CP violation in the neutrino sector hints at the reason the universe is made of matter rather than nothing at all. We do not know which of these hints will turn out to be correct, We do not know what the final theory will look like. We do not know how many more surprises neutrinos have in store. But we know that the crack is real. We know that it demands an explanation. And we know that whatever that explanation turns out to be, it will take us beyond the standard model, into territory that no experiment has yet fully explored. There is something poetic about the fact that the particle pointing toward new physics is the one we can barely detect. Nature did not place its deepest clue in something loud and obvious. It did not put the key to physics beyond the standard model in the behavior of the top quark, which is produced abundantly at the Large Hadron Collider and studied with ease. It did not hide it in the photon, which we see and measure constantly. It placed it in the neutrino, the quietest particle, the one that refuses to interact, the one that passes through matter as though matter were not there. To find this clue, physicists had to go underground. They had to build detectors the size of cathedrals and fill them with tens of thousands of tons of purified water. They had to wait for years and decades, collecting data one faint flash of light at a time. They had to develop analysis techniques capable of extracting a signal from noise so overwhelming that for every real event there might be a million false ones. They had to trust their instruments when the world told them they were wrong, and they had to be willing to follow the evidence wherever it led, even when it led away from the most successful theory physics had ever produced. That willingness to follow the evidence is what science is at its core. Not a collection of facts or a list of equations, but a commitment to letting nature speak and listening carefully to what it says. Even when what it says is inconvenient. Even when it contradicts what you expected. Even when the signal is almost impossibly faint. The neutrino is the smallest known particle with mass, the most reluctant to interact, the hardest to detect. It passes through planets without stopping, through light years of solid matter without caring. It barely exists by the standards of everyday experience. And yet this ghostly, almost invisible particle carries what may be the most important message in all of physics. The message that our best theory of reality is not complete. That the elegant equations we have written describe almost everything, but not quite everything. That somewhere beyond the mathematics we know, there is a deeper truth waiting to be found. Consider for a moment the strangeness of our situation. We live in a universe that is flooded with neutrinos. They are among the most abundant particles in existence. For every atom in the observable universe, there are roughly 1 billion neutrinos left over from the Big Bang, still drifting through space at nearly the speed of light, filling every cubic centimetre of the cosmos. They outnumber the photons of starlight. They outnumber the protons and neutrons that make up every star, every planet, every living thing. In a very real sense, neutrinos are the majority. They are what the universe is mostly made of, at least in terms of particle count. And yet, they are the particles we understand least. The ones that arrived last at the table of confirmed properties. The ones still holding secrets. Every second, the sun pours neutrinos through you and through the Earth. Nuclear reactors produce them by the trillions. Cosmic rays generate them in the atmosphere above your head. The ground beneath your feet emits them as radioactive elements in the rock decay. The Big Bang produced a background of neutrinos that fills all of space, a cosmic neutrino background, analogous to the cosmic microwave background, but far older, dating from 1 second after the beginning of the universe, rather than 380,000 years. These relic neutrinos have cooled to a temperature of less than 2 degrees above absolute zero. They have almost no energy. They are almost impossible to detect with any technology we currently possess. And yet they are everywhere, roughly 330 of them in every cubic centimetre of space, passing through you right now. A sea of ancient particles carrying information from the first second of cosmic history. We swim in neutrinos and do not feel them. And it is precisely these particles, these almost nothing particles, that have cracked open the most successful theory in the history of science. Not with violence, not with dramatic collisions or spectacular explosions, but quietly, through a subtle deficit in a count of argon atoms at the bottom of a gold mine, through a statistical pattern in flashes of blue light deep inside a Japanese mountain, through the patient, persistent, decades-long effort of thousands of scientists who refused to stop asking why the numbers were wrong. Neutrinos are small. The crack they have opened in our understanding of the universe is enormous. And the story of what lies beyond that crack is still being written. It is being written in laboratories underground, in the data streams from detectors buried in Antarctic ice, in the equations scribbled on whiteboards by theorists trying to make sense of what the experiments are telling them. It is being written by people who will spend their careers chasing a handful of events from particles that do not want to be found. And whatever they discover, whether it is the seesaw mechanism or something nobody has imagined yet, it will bring us one step closer to understanding the rules that govern everything. The universe whispers its deepest secrets. You just have to know how to listen.